it for us.
Name is Everett Weakly, Everett Weakley.
Okay, and as much as you can, look at me when you're talking.
Okay.
That's great. Okay, first thing, maybe you could just tell us where you went to school, what your degree was, and how you got to Hanford.
I was hired by General Electric in 1950, right out of University of Idaho, which isn't very far from here, Moscow, to come down here to the heights of the Cold War. Things were coming up. My first assignment was out on the tritium extraction, which has nothing to do with the old days. I was there for a year, and then I was transferred down to the 300 area, working fuel elements. I was there a year, and then went back out to the tritium extraction again, finished that up before they transferred that down to DuPont. And then I spent 42 years in fuel production. I'm a chemical engineer, and you say, what is a chemical engineer doing in making fuel elements? But there's a lot of chemical processes, plus metallurgy is nothing but solid state chemistry anyway. And I became kind of a historian of that. Worked a lot with Michelle Gerber when she wrote up everything about the 300 area. I have a problem with my throat.
Can I get your water?
I'm turned off.
Yeah, and by just a second, start transcription. Okay, go ahead.
So I was worked on the changes in the old reactor fuels starting in 51. And then when they went off and started the one for the in-reactor, I worked on the in-reactor fuels too, so that was over with. And we're here to talk about the Manhattan Project primarily, and I reviewed a lot of the history of that since I was into this business. And when the reactor in the first one that Fermi made back in Chicago in 42 in December, got that going, that reactor was the fuel, the material, uranium, was primarily uranium oxide with some metal. Now, it had been 150 years before that reactor was built that they discovered uranium metal itself, uranium itself. But the process of making uranium was actually very complicated and very dangerous at that time. They didn't have much uranium metal. So when he came up with that this is going to work, uranium is going to work, in 1943, they spent about a year developing how to make uranium metal from the ore. And that Mallinckrodt Chemical Company in St. Louis did most of that work. They had pitch blende at that time with the main ore source from Belgian Congo. Well, the war was on. It was hard to get pitch blende in here, so they had to develop to get the ores from southwest part of the United States. That's a different ore than pitch blende. And Mallinckrodt developed that. They started out by making uranyl nitrate. They heated that, made uranium oxide, UO3. Then they reacted that with hydrogen, made UO2. Then they reacted with HF, hydrogen fluoride, to make UF4, called green salt. That's the color of it. The people in Tennessee at the Oak Ridge process needed UF6, so they would take UF4, reacted with fluorine gas to make the UF6 for the process in Oak Ridge. We got UF4 out here. They sent it out, and so they'd take, the process then was to take UF4, and they would mix it with calcium metal, which is fairly rare, or magnesium metal.
Could you say that again, but explain what UF4 is and UF6?
UF4 is uranium tetrafluoride. UF6 is uranium hexafluoride, which is a gas, which is they needed in a gaseous diffusion plant. UF4 is green salt, they called it, because it was green. And that's what they then used out here in the 314 building. That's where they finally made these started. So they'd shipped the uranium UF4 out here, and they had a process. They put this in a bomb, and they mix it up with calcium metal for a while. That was hard to get. And then they switched to magnesium metal, which is a little bit easier to get. And they would mix that up, put it in this so-called bomb, heat it up, and the reactor would be exothermal and take off, and you end up with molten uranium, which would float to the bottom, would sink to the bottom, and then the calcium or magnesium fluoride would float to the top. They would quench that, and they'd come out with what they call a derby, about this big around, weighed about 350 pounds. They would take these derbies, a couple of these derbies, and after the process was going, they'd have rod ends that they talked about from machining the cores, and they'd have briquettes from the chips that they compacted. They'd put all that together in a vacuum furnace, and then they would melt that up into a billet of about 1,200 pounds. And then they would use that billet, they would machine it down, and they extrude it or roll it, depending on the process that they wanted to use it at that time. They would either gamma extrude it, which is a phase of above 770 degrees centigrade to melting as a gamma phase. That was the easiest to extrude in. And then what they called alpha phase, below 660, in the alpha phase of the uranium, they would roll it. They would send that off site to roll it, and then the rods would come back. So the early days was gamma extruded here. Now uranium, as I said, had 3 different phases, and the one up to 660, the alpha phase, is a complicated orthorhombic structure. And if you heat that, it changes, it'll grow in 2 directions and shrink in a second direction. And this made it very complicated for making fuel elements because they had to control that. And so they found out in the metallurgy, looking at the metallurgy, they had to heat it up into what they call the beta phase. And the beta phase, between 660 and 770, they would then quench that back down, and that would randomize the grain structure, so you wouldn't have the fuel element growing in the reactor or making pimples out the side like an old cucumber. And they had to it would stabilize the uranium. Now, in making the fuel element for the reactor, there was a lot of requirements that were put down by Fermi. It had to be, processes had to be that you could get commercially. You had to have it clad with something, so that they picked aluminum. It had to be bonded, so they'd have good heat transfer between the uranium core and the cooling water. You couldn't have any voids, or you'd have a hot spot. And if the water got in to the uranium, it rains uranium oxide in a hurry, and it blows up, and you have a failure. And you would contaminate the water. You'd have to shut down, discharge the reactor, clean things up a little bit, and it would delay your production. So they had to have a good bonding. Now, they tested a lot of things here at bonding in the early days. They tried zinc, and they found a bunch of other metals. They had something called a whiz-bang machine, which didn't work very well. You probably heard of, if you wrote any history, you heard about a whiz-bang. And they finally came up with the triple dip process, which was talked about a little while ago by John Smith.
Tell you what, why don't you take a quick drink and then start with the triple dip process, because that's an important section.
The triple dip process was developed finally and proved beneficial. And so what they did, they took these uranium rods in 313 and they machined them. In fact, when I first walked into the 313 building, when I first got here, I looked at all these lathes with the rods, and they were machining them. And there was a fire. Every one of them, there was a fire going all the time from the chips. They were pyrophoric. And then it was pulling off the uranium oxide smoke. And I thought, boy, this is kind of dangerous looking. But they controlled the smoke, but it's pyrophoric. And so that's one of the dangers of uranium. It is pyrophoric. It had to be protected. So what they did, they machined them at that time into 8-inch, about 1.4-inch diameter, 8-inch at that time they started out, solid pieces. And so when they got done machining these, they would send one over to the test reactor, which was built and got going in, I think, February of '44. They would test each one of these rods, make sure there wasn't some impurities in it, boron or cadmium or some other high cross-section element that would poison the reactor. So every rod got checked, at least one of them out. Anyway, they take these elements, these solid pieces, they would etch them in nitric acid. And that cleaned off the oxide just before they went into the canning bath, and somebody would inspect them for cracks or anything else that was harmful looking, and before they put them into the triple drip process. The first bath, as it was explained, was a bronze bath, which is a copper tin mixture, and it was up in the beta phase. This is the way they controlled the structure. They got it up into the beta phase and held it there, and then later on in the process, it was quenched back down into the alpha phase. And that bronze bath was covered with a flux, a chloride flux, and so that would help bond, so the bronze would tack and start making a structure on, or what do you call it, bond? Well, it's a bonding, I guess, with the bronze. You'd have a layer formed of copper and tin on the uranium. And then they go over and they washed it off in a tin bath, a molten tin bath, and wash off some excess bronze. They went to this centrifuge that would whip off the excess tin. Then they went to the alci bath where they assembled them in the aluminum cans. Now the aluminum cans were cleaned, chemically cleaned, so they wouldn't have any oxide on them, and they were put in a steel sleeve. And the steel sleeve was cleaned also, coated with soap, and then they would put this can in there, and they would stick it down in the bath with the can open, the top, preheat it, and then just before they brought over the fuel elements, they would submerge it. And then they would stick these coated fuel elements down inside, and somebody else had a cap that's been cleaned. They would push that down on top of that. They were then taken over to a quench tank and quenched in water so they wouldn't stay there long enough to melt through the aluminum. So you'd have a good aluminum structure, and that's bonded. Then you'd have the aluminum, you have the alci, you'd have the coating of the bronze on the uranium, and they have uranium. That was your layer. When they came out of the quench tank, they took them to a radiograph machine, and they would measure off the distance they wanted that cap to be. They could see the uranium. They would measure off, say it's a half inch, say, and they would make a mark. They would machine that end off down to that mark. And then they put a weld on it to cover up that braze, the alci, and mix it with the aluminum, so you wouldn't have a porous, brazes are kind of porous. You wouldn't want metal, uranium to get down to water contact. That would cover up that braze, so that would have a nice welding, and that was a heliarc welding. And then they went through, they had to make sure there wasn't a bunch of voids in the braze metal. They went through something called a frost test. And a frost test, they dipped these fuel elements down into acinaptylene, which is in carbon tetrachloride. They brought these out. The acinaptylene would coat this core, this fuel element. It would coat it, and it looked frosty when it dried. Then they sent that coated fuel element through a induction coil. When the induction coil would add heat to the outside into the aluminum, if there was a void or in that bonding layer, you get a silver spot. And they call it a frost test. They have a nice spot, and everything else is frosty. So if they'd look at that, if there's a spot there that was shiny, they would reject the fuel element. If it passed that test, they then went to nitric acid solution to take off. Well, they started out with it. Before that, they had to go through a degreaser, would take off the excess frost, and then they tested nitric acid. They went through a weld inspection, and they looked it all over, and then they went through an autoclave, which simulated the reactor, so make sure there wasn't any holes anywhere in the weld bead or anyplace else. If the water got in to the uranium, it would catastrophically blow up, and you would have a failure in the autoclave instead of the reactor. And that's where they would want those, not out in the reactor. And then the last thing they did was they took an X-ray of the weld bead and checked it for voids. And then after that was done, they made a final inspection, put them in shipping containers, and set them out to the 100 areas. And that's the process, basic process of the old triple dip process. After that, we went into other processes. We changed. We had to change the length from 8 to 4 when as the one person said, the process tubes distorted because of the growth and the graphite had changed. Until they solved the growth of the reactor, of the distortion, they stayed at 4 inches for a few years. They went to 6 and back to 8. And later on years, we had a lot of 6 inches, but they were different kind of fuel elements. They had higher enrichment. When we first started out, we had nothing but natural uranium, 0.71% U-235, which is the reactive part. When they started getting some enriched uranium, they upgraded ours to 0.95. So most of our fuel elements were 0.95 in later years. And then we had some 1.25 for target elements and some 2.1 enriched for making tritium and same thing. So we had our ways of enriching, but that was later on after the Manhattan process. Let's see, is anything else you going to quiz me?
I was wondering about, you mentioned that Malincrot took a full year to figure out how to make the metal. So that was 1943.
1943.
Right, and then how long did it take to make all of the, 2004 fuel? Well, those are the rods, so there are many elements included. I mean,
they had it took them quite a while to get a good first batch out. I think it was something like in June they started really canning, June of '44, and they got the first load. Took them, and then all this business about the whiz bang and whatnot, and trying to develop it took them a while to get down to the process was safe enough that they would say, hey, we'll put these in the reactor. And I think they were out there in about September. They got a full load for a B reactor, for instance, which is the first one loaded up. And they did a lot of recycling. Now the cleaning, to recycle a fuel that's a reject, and so they did. They had a lot of rejects at that time. They would take the fuel element, they had to dissolve the aluminum off in sodium hydroxide or caustic. Then they had this compound layer, which was a copper, tin, uranium compound layer. And they used hydrofluoric acid, which is kind of an odd one. And that would dissolve off the bonding layer. Then they would put it back through the process of nitric acid, inspect it, and put it back through the process, the core. So they would use those over again. Of course, the aluminum is gone.
so at first, what percent do you think were?
Oh, it took them quite over 100% for several months until they got the process going. Oh, yeah, there was a lot of work out there before they got going. There was a lot of concern whether they were going to have enough fuel, a good fuel, to load the reactor. And they solved this by putting the triple dip process. And there was some frantic work out there, I understand. Most of those people that worked on that are gone. But I've heard, talking to some of them in the old days about that process. And, it was quite a. Now Lou Turner worked on it, but he worked it back east, and they didn't come up with that process. It was done here.
Could you explain what an autoclave is? 'Cause
An autoclave is a steam autoclave that came up with the temperatures and the pressures to simulate
Hang it.
in reactor.
Start again,
You need to
because
start
he was
again.
talking at the same time.
Oh, okay.
Go ahead, tell her.
Okay, an autoclave is to simulate the reactor. They put up a steam and at a higher, actually a little bit higher temperature than they're going to have in the reactor. And if there's any failure, like a little crack or a pinhole through the cladding, that steam would get through and react with the uranium and blow up. I mean, it would actually just disintegrate. Usually you end up with all you have is a little bit of aluminum and all the uranium is in the bottom or is a uranium oxide. And that's what they don't want to have out in the reactor. They'd rather have it down here, which you wouldn't cost you that much. And you can clean it up, clean up the reactor, it's a mess out there to clean up. Here you clean up the autoclave and you're ready to go again. Get the uranium oxide out and recycle it. And
So the autoclave was made as a big cast iron furnace?
it was a great big, they put about 5 baskets. And then it was probably 12 foot deep, and they were down into the floor, and it was with steam, high pressure steam, and it sat in there for hours, several hours, till they got up to temperature, and they bring them out, cool them off, and then inspect them. Once in a while, there'd be a small hole, and there'd just be a bulge on the side, but most of the time it disintegrated all the uranium would be gone. But that was just to protect the reactors.
Did they try various cladding materials?
They clad aluminum was picked because it's commercially available. They didn't have zircaloy 2 at that time. It wasn't even available. And so that was the cheapest and less cross-section material they had. It had to be commercially available. And it worked. Essentially 2S aluminum. Later on they had 12-14 alloy, which was a kind of an iron control, and then they went to M3 at 388, I think it was. That had a little bit of nickel iron in it for the corrosion of the aluminum itself. Now they control the corrosion of aluminum by controlling out the 100 areas the water treatment. They would treat the water so that it wouldn't attack the aluminum quite so bad. And that's where the sodium dichromate came in, that you probably heard about when we talked about the reactor. That was to control the corrosion of aluminum cladding.
Just characterize what was going on at that time with the people, because it seems, as we go through these interviews, we end up with, there are 50 really critical little, I'm going to call them tricks, that people came up with, like the aluminum and then adding the nickel and things like that. What was the atmosphere like there out there? It was kind of a creative scientific atmosphere, wasn't it?
Well, we kept trying, making improvements as we went for years. Right up to the very end, even when I was in reactor fuel, we tried to make improvements for increasing the production, increasing the quality throughout. We had to. That was just the way it was, a way of life. We would change the process. We went from the triple dip to the lead dip process, and we were able to do that because we heat treated the fuel elements in bare form before they got into the, didn't need a triple dip bath, and they didn't need that bronze bath that was up in the beta phase. Everything was in the alpha phase then, like around less than 660, about 590. And so we were able to can everything in the alpha. And then you could make a larger fuel element. You didn't have to work, because there was some distortion when you beta heat treated. So you have a little bit more uranium per foot in the reactor, and that would up your yield. And then they kept changing the power of the reactors, up and up and up and up, temperature.
Can you sort of very briefly explain these different phases, the beta and the alpha?
The alpha phase is up to 660. You got an alpha phase, an orthorhombic, very complicated crystalline structure. And as you heated that, as I said, two directions it would expand and one would shrink. And if you extrude it, you'd have those little grains are all oriented. And if you put that, did not heat treat that, that would blow the cap off in the reactor. Either blow the cap off or it would punch a hole out the side like a cucumber with a pickle, how the cucumbers have go out the side. And so they had to put it up into the next phase, which is the beta phase, and then it would quench it back down, and that randomized the grains. And if you went far above 770, you're in the gamma phase, and that's the phase that they like to extrude in because it was easy extruding, like extruding toothpaste almost, compared to back in the alpha. Alpha, they rolled them in alpha, but they extruded them in the gamma phase.
So that meant in the gamma phase extrusion process, you had to have it at a certain
Temperature, above 770, below 1130, which is the melting point. In between there was a gamma phase. Somewhere in there you would do the extrusion.
And can you describe the extrusion presses?
Those were done back, well, we had a few small ones here.
You use the word extrusion presser.
Extrusion press, they have a billet, and it goes down through a die to come out to the size of say, 1.5 inches, which is the rod you want to machine down to 1.4. So you go through a die, so you still end up with a billet, a 1,200-pound billet, and then you end up with a 1,200-pound rod, but it's several feet long, 20 feet long or 18 or whatever it happens to be. And it was that simple. Now they took all of these rod ends, you'd have rod ends and machining chips, and the rod ends would be remelted, and the chips, like we were explained, were compacted, and then they were sent back to the remelt plant in 314 and goes back in and put in and melted up again with derbies from the green salt part, and then remelted and then extruded again, or sent offside for rolling. We didn't have the rolling prop here. We sent most of those offside for the alpha rolling. But we did do the gamma extrusion here for a while. But in 1952, practically all that metalworking was done at Fernald in Ohio. So everything was done then back there.
And during the Manhattan Project, it was done partly at Hanford and partly...
Most of it was done here for gamma extrusion. If they wanted to roll it, they sent it off to some other outfit and they rolled it for them. But most of it was done gamma extrusion here. They did a little bit of both, and they both worked.
Can you discuss the pyrophoric quality of uranium and how that affected the machining of it and working with it out in the 300 area?
Well, if the pyrophoric, the chips would catch on fire if you hadn't, and usually you had water and, water-soluble oil sprayed on them, but you had to watch that. You had to watch that all the way from there on because of the, you didn't want to have a fire shut you down. And but we controlled it mainly by just submerging it under cooling water, which had water-soluble oil in it usually, and that would smother it down and control it. We had very few fires. We had no fires that would shut us down, but we did have little chip fires. When you were machining, you had to. No way you could get around that. And later on, many years later, when we got into zircaloy 2, that was pyrophoric, and you had to watch zircaloy 2 from burning too, because zirconium will burn also in fine form. But the uranium, that was the first thing that impressed me, was those fires going in those lathes. So I walked through and, but they just sort of smothered them out with excess cooling water.
Just so that when we edit the tape, we could insert this. Could you just say uranium is very pyrophoric?
Oh, yes, it is.
Means, but no, you say that for the camera.
Oh, yeah, uranium is very pyrophoric, and you had to watch it. You didn't want fires going, especially the fine. The finer it is, the more pyrophoric it is. If you have a real fine powder, it'll catch on fire spontaneously. But the chip is a little bit harder. You have to have really the action of the heat of machining it to get it to start.
And talk about, they laid out specifications for what the fuel rod should be, or canning process.
Well, the B reactor and the other old reactors were fixed as far as the size of the tubes. The size of the tubes then said how, and then how they had to have much water. The size of the fuel element, which is about 1.4 inches in diameter, in that range, and the length. They gave them that. Those are the process, what they gave them. They had to work with, and they had to have. Of course, we talked about had to be clad in aluminum because that's the only really commercial thing they had available at that time that would really work, and low cross section. They could not have any high cross section materials around, and everything that went out of that reactor practically was checked in the test reactor in 305 building to make sure that they didn't have impurities such as boron or something like that was high cross-section elements. And as I said before, all of our fuel rods, that one fuel core was checked in the reactor to make sure something hadn't got in accidentally and contaminated the uranium with a high cross-section material. And boron is one of the biggest ones, of course, they'd worry about. And but they had to make that fuel element and to protect it from the water. It had to be bonded, etc. They tried a number of different things. One of them was zinc, and that didn't work. And then they finally the Alcide process came up, and that did work. And as Lou Turner was saying, they were trying things back at the same time in Chicago, trying to come up with a method of bonding that. And it was developed here finally.
It was the fact that they used some rods they rolled in the alpha state and some they extruded in the beta. Was that an example of this?
No, they did not extrude them in the beta. They extruded them in the gamma,
Okay.
and they rolled them in the alpha. Okay. That was the way it was easier, because it's easier to roll something in the alpha phase, and it's easier to extrude it in the gamma phase. They did not try to work that in the beta phase because you only had 660 to 770, which is too short a range to really get work in. You'd be going back and forth. That's where you went in and heated it to change the structure so it wouldn't deform in the reactor when you got done canning, in the canning process or before.
They tried both the extrusion and the rolling to try to experiment with what would work. They didn't know which was best.
Well, yeah, they were trying both, yeah, right. Mm-hmm. Right. They used a lot of gamma extrusion out there when they first started in the 314 building. Later on, they went to alpha. That was off-site. And then when they went to phenol, they went to the alpha rolling process. But then, at that time, they also changed, and they heat-treated the cores before they came to Hanford. The cores were heat-treated by themselves, back up into and then back down. And we didn't have to do that. That's why they changed the process from triple dip to what they call lead dip, and that cut out made the canning line much simpler. We only had 2 canning pots: a lead dip covered with Alcide, and it was it was less than 660, and then a canning pot, and so it was a lot easier. And it didn't grow. The uranium didn't change shape, and so you had more uranium per foot than you had before. You make the diameter of the uranium a little bit better. You're waiting for the distortion of going into the beta phase. And so that's one of the advantages that we switched. But that was not until in the early 50s, long after the DuPont.
What about the canning line? How many lines did you have at once?
Well, the first started out, when I came there, like he said, I think there was about 2. And then shortly after that, we ended up with 6 canning lines. Had an expansion. But that was primarily when we went to change our process from the lead dip. We had 6 lead dip processes going. That was in the 50s. And we put out, we can put out 6,000 fuel elements a day when we start in the lead dip process. Because we had 6 canning lines, you got 1,000, but it was a 2-shift operation. That's maximum. We had that back when before that, we didn't have that many reactors. We didn't have the K reactors. We didn't have, and we didn't have some of the other ones that weren't built yet. And but that was the maximum. But that was lead dip process. Triple dip, there wasn't that many. Like you said, it was about 2 canning lines. It was slower. I was there during the transition when we were going from triple dip to lead dip.
During the Manhattan Project, were they able to keep up with the demand for new fuel elements, or was that a?
They had trouble at first, but then they got in the swing of things, and they had no problem of keeping up with the production.
How they get the slugs from the 300 area to the 100 areas?
Well, they didn't send the slugs out. They sent fuel elements out that are canned. The slugs are usually the bare ones, and they were shipped out in boxes, in shipping containers in a truck, and they shipped those out in the truck. Had spacers in there, and they shipped them vertical, and filled up this semi-truck, and out they'd go. And then they'd unload them and bring the empty boxes back, and we'd fill them up again. I don't remember how many. There was 100 and some, I think, in one box. But they were just little pigeonholes set in there. They wouldn't hit each other. And
was there any concern about criticality as they were being shipped from one area to the next, that there might be enough for these fuel cells?
not on this.
Tell her.
Not on this enriched, unless you had enriched uranium.
You need to, because we're not going to hear the question, so you need to start with what it's about. In other words, say, there was no concern over criticality.
There was no criticality problems in ship.
I gotta finish talking.
Okay.
Go ahead. Go ahead.
Okay. A question was brought up: is there a problem with criticality in shipping these fuels out? No. There's no criticality problem unless you had a reactor wrapped around it, and it's hard to get one of those, and that's a lot of tons. So we had no critical problems in shipping fuel elements to the 100 areas in shipping boxes. You'd have to have very highly enriched problem to have any criticality problem on shipping out to the 200 areas or 100 areas, and you'd have to have space. You'd have to have moderators and so on to make it critical, and you have to have tons of it in the early days. If you have highly enriched, then you'd have to worry about criticality, but we did not have that in the early days.
A good question, then, which follows up on this, because, we're trying to explain this to lay people as well. So could you talk about what the composition of the fuel elements was?
Okay.
So to differentiate that between the U-238 and what could go critical, the type of uranium.
The only thing we had and started in the Manhattan process was natural uranium, and it's only got 0.71% U-235, which is what goes critical. Okay, so there's no way you can get that stuff to go critical without putting a reactor around it. Later on, after they started getting some enriched uranium in from Oak Ridge, then we went up to 0.95 was our standard. That still, you could not get that critical. We had a few elements up to 1.25 and 2.1 and for when we have target elements going in and out in some of the reactors to make tritium and to make some of the other isotopes that they wanted for space programs and whatnot. But even that stuff, you could not get critical in that form. If you had, we had some elements that were high enriched aluminum elements that were taken out there in the 50s and 60s. Those you watched a little bit closer because they were essentially bomb grade U-235 with aluminum in an alloy form. We did watch those closer, and you could get those. But they were shipped out, usually separate, in small quantities.
Because I think that's a common question. People say, well, if you put all that uranium together in one place, isn't it gonna go critical?
No. It will not go critical if you put all this uranium in one place, unless you have a reactor around it to control it, to space it, and moderate it. You got to moderate it with the graphite.
Could you talk some about the PPE requirements for handling the uranium, if there were any?
What's a PPPE?
Personal protection equipment. I mean, what were guys dressed in when they were handling and shipping the uranium?
The operators normally wore coveralls in our area. They really didn't worry too much about uranium. They have to wash it off. It wasn't like something that's highly contaminated like, say, tritium or plutonium or anything like that. So those people had white coveralls on usually, and they would change them in the back in the change rooms, and that was about it. I wore a lab coat most of the time, but it wasn't that much problem with uranium that's unirradiated. Now, back in the machining areas, they had step-off pads and whatnot to keep the people from getting contaminated and taking it home, whatnot time thing. And they would check them out in certain areas, like the machining area, make sure you weren't getting your hair contaminated or something like that. But it wasn't that bad. They just make them take a shower. It isn't like being out in the 200 areas where you have high plutonium or something like that. Uranium wasn't considered that much of a hazard at that time.
Yeah, that was a point that I wanted to have made, is that there was a big difference between handling uranium and before and after the irradiation.
Oh, yes, after radiation, yes, it's highly radioactive. After radiation, then you have all these other byproducts, these high intensity gamma radiation, beta radiation. Uranium is alpha. Alpha you can stop on a sheet of paper. Your skin stops it. It isn't like something with a gamma or beta. We didn't get into much of that, fortunately. That's why we had hands-on. You could pick it up, the bare uranium, but most of the time they wore gloves. But if you picked it up with the bare uranium, you still wouldn't get radiated because your skin would stop it, the alpha.
What kind of monitoring was done on your exposure? Was there any?
Well, they had monitors there in the building, but and people had step-off pads. They could check their hands when they come out of these places where they had machining. You know, they'd check and make sure they weren't packing it off and around the building. And they had shoe covers on. They would take off. Oh yeah, they had the monitors there. But it's not like out in 200 areas where you had plutonium, which is poisonous to your system more than uranium.
From what you heard about the Manhattan Project, what was, and your own knowledge of it, do you want to comment on what you think was, from a scientific or engineering, technological development point of view, what was marvelous or impressive about that at Hanford, about what they did in the fuel canning area, or the?
Well, the whole thing, by getting it out in time to stop the war, before we didn't lose all the people, soldiers.
Start with the Manhattan Project.
Well, that's what I mean. That's the Manhattan Project. If we hadn't had the Manhattan Project, we would have lost, I don't know, hundreds of thousands, maybe a million men trying to get the war over. And then we got into the Cold War, and that was a race to develop the hydrogen bomb and other bombs. But you look back at those old B reactor and the old reactors, you wonder, those people really had to have insight to build something like that would work the first time. From that little old reactor that they call it in Chicago, with a little bit of uranium oxide and a little bit of very little uranium metal, and say, hey, this works. And then to scale it up to the old reactors was phenomenal. Once they had the old reactors going, then the step up to then the next reactor phases like the Ks, and then the N reactors was just matter of development. A little bit easier step.